Welcome to today's Sendo Reliability webinar. This is Fred Schenkelberg, and hopefully keep my fingers crossed that everything stays in working order today. A whole lot of changes in diagnostics over the last couple of months, and still haven't really sorted out why my machine crashes every now and then like this, but we'll keep our fingers crossed and drive on. But today's topic is one of the basic tools, one of the things that many of us have probably used at various times and places, and hopefully pull it out when it's the useful thing to do. And as I was mentioning just before we got started, is I really don't remember the first time I ran across it, yet it's been one of those, it's like a screwdriver or a pair of pliers in my shop. It's something I go to over and over and over again when taking a look at a set of data. It's just a fundamental thing that can be used. Yet when I started thinking through the basics, the concept of it, and all that stuff, there's a few things to keep in mind, and that's what I wanted to talk about today. Now, it's a great way to visualize a set of data. So if I've got just a table or a list or even a check sheet that I'm marking observations on, it's a great way. This Pareto chart is a wonderful way just to get an idea of how it looks. What can we learn by just doing a plot? And many of you have heard me say it many times, is that when you get a set of numbers or set of data, plot it, visualize it, get it in some form so that you get a sense of what's it about, how's it set up. Now, the Pareto chart is a little different than, say, just a classic bar chart or a histogram or something like that. We'll get into some of those differences. Yet that subtle difference that we'll talk about really helps you make astute, I guess is the right word, observations and conclusions about the data set you have. And we'll obviously talk about that in a bit more detail. But it's the analysis part isn't just the chart. There's more to it than just creating a chart. And the process starts before you even get out the table or the spreadsheet or whatever to make a chart. It starts well before that, and starts really with the data sets that you have and how you go about collecting those and how it's organized and so on. So the analysis part of Pareto analysis starts very early with your data collection and what question you're trying to answer. What kind of decisions do you need to make? All the way through to drawing conclusions and checking your assumptions and so on. And we'll go over a handful of pieces of that overall analysis. The other part of this is there's a downside to Pareto. I've heard it, and I'm sure you have too, is saying, oh, it's just the 80-20 rule. Well, the issue is that I hear that phrase and, oh, we're going to solve, the top 20 defects that we find, and that'll solve 80% of our problems. Well, maybe, maybe not. It's not a rule like gravity is, right? It's not a law, that nature's law that this always happens. The number pi shows up in a variety of different situations, and it's surprising how many places it shows up. And E is another number that we deal with that shows up in all kinds of cool places. Yet it doesn't always work. You don't need pi to understand the circumference of a square. It doesn't really help you much. So it really depends on what you're trying to do and a handful of other things. Yet what I found, and it's, I don't know, irritating at best, is that, oh, it's just the 80-20 rule, we're done here, or that's the only thing we need to do, and so on, with which is fine if you've got the supporting evidence, if you've got the chart or the analysis that says, yeah, that is really actually true. Now, I picked ice cream cones, one, because it's blazing hot out here where I live at the moment, unusually hot. And ice cream sounded like a good idea yesterday afternoon. And I went looking for the favorite uh, ice cream flavors, by volume. What types of ice cream flavors are bought most often? And I was expecting that 20% of the list would cover 80% of the volume of ice cream that's sold, and that wasn't true at all. It I saw one list that was like the top 100 flavors, and I thought, well, I'll add up the first 20 there and see if that rules the day. And no, it was closer to like 30 to 40% of the volume was in the top 20. Apparently, some things don't follow this rule. And so the idea is that it's a useful concept when it's true. And if it guides our expectations to overlook what's actually happening with our information, with our data, well, then you're kind of skipping ahead in assuming that it's following that rule, the Pareto principle or the 80-20 rule. That's a problem. And so I want to make sure I highlight that, and I'll come back to it in a little bit more detail later. So let me ask you, in the chat or wherever you're comfortable with, chat or the question tabs are the two that I'm watching. How do you use this stuff? How do you use this? What kind of situations do you pull it out, or is it an ongoing tool that you always have in place and on a dashboard maybe? Or is it a one-off thing, or is it some other application that you use? Where do you use this? Yeah, field failures. That's a good one. Month of returns, general guideline, return reporting, biggest driver of an effect. Yeah, all good stuff, all excellent stuff. It is a versatile tool. There's no doubt about it. Yeah, thanks, Sebastian. Revenue by customer. Oh, that's a good one. I like that one, Murray. Yeah. Although I always look at it as if you only pay attention to 20% of your customers because they generate 80% of your revenue, you're missing out on the other group that are soon to become your biggest customers. Which one do you pay more attention to? And it's kind of a salesman's dilemma, isn't it? All right. So a little bit of background. I did find a picture of Vilfredo Pareto, which I'm sure I'm not pronouncing right, but he was a economist in Italy in the late 1800s, and he observed, among other things, that there's a handful of people that own most of the land, and I don't know what his politics were or what the reason for the observation was, but there's actually a paper out there that talks about it, and it's an economics part of thing, and I think he was, from what I could understand of the paper, that it was kind of like, this isn't really good for the country as a whole, for our overall prosperity as a nation. And I think he was making that kind of a point in this observation. And then it turned out that, that observation, this 80-20 kind of thing that it came up, pretty much went away. It was pretty obscure until Duran, and many of you may already have a copy of Duran's quality handbook that's 2.5 inches thick or 3 inches thick or something like that. He named this concept, this 80-20 rule or the Pareto principle, after Vilfredo, and it then caught on. At the time that we had the fishbone diagram, that got named after somebody, I think Ishikawa, and so on. I think Duran was behind a bunch of that kind of stuff. It might have been just pure marketing, or it might have been given him recognition for having made this observation, and that seemed to work in a good number of areas. And it got generalized a little bit, but it's not that old of a, well, I guess over a century old idea. But it also comes along with that we're starting to make observations. We're starting to collect data and information in a more systemic way in lots and lots of fields. And so people started noticing this kind of 80-20 thing, but also lots of other things that we've learned over the years. And in general, you can count on that 80% of the consequences or the outcomes or the results can be attributed to 20% of the causes. And therein lies a key piece. I mean, we could do 80-20 all day long on pure coincidences, right? And if we look hard enough and search hard enough, is how many home runs are hit and how's the stock market do that day? In some sequences, just by coincidence, that it's going to line up, that certain teams will have more home runs and the market will go up, or some other meaningless correlation or coincidence. So it's really contingent on, is there a causal link of some sort for the way we typically use it, right? And part of this is that it's the causes. And many of you have done root cause analysis to where it's pretty meaningless. We just swap out the component and hope for the best. Well, what caused that component to fail? And a whole bunch of other downfalls to this is if there's not really a good linkage in your data set, if you're not counting the appropriate things, and then making a nice chart of it, you might come to conclusions that are pretty meaningless. So keep in mind that, if 80% of the deaths in traffic are caused, are related to or caused by speeding and over the speed limit, for example, that may or may not be a true statement, yet it's that kind of thing. Is there a relationship there? And if you have that kind of question, this concept may help to correlate it. Now, in some cases, if you've got variable data, Pareto's not all that terribly useful. If you really are looking for a correlation, well, do the regression analysis and look at your correlation factors and see if there is really a relationship between the two variables you're interested in. Which brings up that, we're dealing with random numbers with most things that we're dealing with. And the first step in dealing with applying the 80-20 rule or doing a Pareto analysis, is there some causal linkage of some sort, some meaningful relationship that connects the things that we're binning these items into in different counts, or not. If there isn't a reasonable relationship, then we're pretty much playing with just pure random coincidences types of things and may not get much of any kind of a realization or valuable information out of the process. So it's the key point is to understand what it is you're measuring and trying to plot. Now, a couple of you mentioned, how you use it is in field failures, right? That's one of the early ways I've used it. And I've used it in a handful of other ways where it's really dependent on how we categorize the types of failures. And I think that's a very key rule here, is that how we bin or categorize what we're dealing with and what we're counting really, really matters. So the really first part of a Pareto analysis is thinking through what is it you're actually working with. And we'll come back to this field failure problem or even diagnose, if you're working in a factory, what's the downing causes of the downing events? Well, how do you actually collect that information and what is it meaningful or not for you? So I think I've got a leftover from my last webinar was what is hypothesis testing? Well, that has nothing to do with what we're dealing with here. I think I forgot to change some titles. But the last piece in this history is that sometimes this is called the law of the vital few. And it's the idea is that if we focus on the things that cause the most problems for us, for example, if we have, say, a power supply that's, you know, causes the most failures in our in our product in the field, well, it just goes to common sense that, oh, geez, we should probably sort out what's going on with that power supply and fix it. And it'll reduce the overall number of field failures we have. That stands to common sense. And it's the idea is that if you knock out those big hitters, so to speak, that we're making progress. And there's nothing to argue with that about. Now, there's a handful of problems like checking whether you have the slides titled correctly or not. I guess I missed that, the many trivial, I guess. Um, Yet it gives us that concept that, and I know that Chris Jackson talks about it a lot, and I know that Carl and I and others in the field talk about it, is in the process of product development or process improvement or in improving availability, there's usually a very good argument that a handful of things, the vital few, are the ones that deserve our attention to make the biggest return or improvement in our process, in that product or in that factory. The idea is sound. There's no doubt about it. And it helps us provide focus. And that's one of the biggest benefits I find with the Pareto analysis is that if we're all just looking at a set of data, and I've run into this where the electrical engineer says, oh, it must be the capacitors. We got to deal with that. And the mechanical one is go, oh, no, it's vibration. We got to deal with that. And they each go off in their own tangent of how they view the product or the system and what areas they're most interested in solving. Well, if we take a look at some data and say, well, what is the actual underlying causes of the problems that we're having? And Pareto chart may be the perfect way to display it. It may become very, very clear that one of those two causes, capacitors or vibration, may be the issue, or it could be something completely else, something completely different. So it's one of the many ways that we have to allow us to get the data to help set priorities across teams that may have different views of the system or different priorities and different skill sets. And so it's a great way to build some alignment or focus for an organization or for a team that's working on something. It's I think, one of the biggest benefits of it. Right. I know I wrote this a couple days ago. It's like examples of the 80-20 rule. In the field failures, the ones that a couple of you mentioned, sales by customer, I guess land ownership in Italy at the late 1800s. I have no idea if that's still true or not. I tried to get, as I mentioned, the ice cream one, and it decidedly was not 80-20 rule. The bulk of the ice cream sold, at least in the US, I expected vanilla and chocolate, those two to take the vast majority of it. No, they took very little of it. And then I went looking for, well, how many types or flavors of ice cream are there? And I found a site that listed over 1,000 with more added every day. Top of the list was bacon ice cream, which I'm not going to go run out and try to find as much as I like bacon. I've had garlic ice cream, and I wouldn't put that in the top 20 of my favorites by any means. The idea is that it's a concept that really does help us in some cases to focus in on the most important things. But I hope that in the examples that you've used and many of you have talked about is, well, which ones are, which areas, which pieces of this deserve more attention for us, whether it's to improve something that's already working or to improve something that is troublesome or causing unwanted outcomes. Let's see, I'm looking at Jose's got one. Identify major contributors and maintenance and occupant calls. Too hot, too cold calls. Okay, that sounds like an apartment building kind of place. Occasion to identify field failures for modeling. Yeah, where to focus on learning more about them. Returns reporting. Got all those. Yeah, I like the idea, Carl. Finding the best assets and using them efficiently. That's good. Headquarter building in DC. Cool. Right. Let's see, too hot or cold, too cold. Imagine this time of year, it's too hot. All right. So let's talk about just going about the really fundamental piece of how to build it. Well, and as I mentioned earlier, it's all about the data, right? And if I was going to do a Pareto on ice cream, I would go out and personally collect a lot of that data and make sure you had plenty of samples. Best on a nice warm day. The idea, though, is that we need to observe the data, and it's usually count data by some category. And any of you that have made a histogram and then said, well, what if I change the bin size on a histogram? What if I, instead of going every 10 on, say, a number line of over 100, I bin it every 10? What if I bin it every 15? And I did that one day, years and years ago. I said, what happens if I change the width of what gets counted into each bin? And I expected, and I had, I don't know, 1,000 or so data points that I was simulating off of a normal curve. And I thought, well, this should not fundamentally change the shape of the histogram. But it did. And the less data you have, the more it changes the shape of your histogram, the actual profile that it sketches out. And so care needs to be taken in setting up what is your categories. You know, I'm going to use an example on the next slide of, say, a computer system. It has a CPU, a hard drive, a power supply, stuff like that. Now, that may or may not be useful. If I'm just buying all of these subsystems from different vendors and assembling them into a computer, that may be the lowest level that I can act on, right? Now, if I'm designing it and putting my own circuit boards together for the power supply and all the other components, I'm actually building it or having a lot of influence over the vendors on how they build it. I may need more information as to, is it a interaction of some components, or is it a manufacturing type process? What is the next level of causes that's occurring? So part of it is what category am I putting this in? It might be subsystems. It might be machine, on a factory line. It might be which machine it is. It might be a bending machine or a stamping machine or a packaging machine. But is that actionable for us? Is that where we want to stop? Because if I know that the bottling machine, the most complex one that we have on the line, is causing the most problems, well, what do I do with that? I can go study that machine and get more details about those things. But if I don't collect information that's underlying what's causing those downing events, well, that just starts a whole nother project, and I reset what I'm gathering. Now, the category, say, for that bottling machine, it might be, is the empty bottles coming into it, are they the right dimension? Are they the right speed or the right orientation or whatever it is? And it could be in the alignment process. It could be in the filling and sealing process. It could be the capping process. We might break it down into categories like that, or we'd get it down into motors and gears and sensors and timing and the next level of it. The basic idea here is that the data that we collect starts with what we're trying to do. It's what information do we need that we can take action on. And going back to the field failure issues and stuff, that works great as a starting point. And if you're starting it, like I'm going to do on the next slide, at subsystem level, that gives us an area of focus of then go do a set of data collection, say just on those power supplies. I always pick on power supplies, by the way. And then we have something we can act on. It may be a cascading set of data collections as you focus in on, well, what can you do about this? As all of you know, power supplies can fail for many, many different reasons. So what do we fix if we just happen to know that power supplies are a big problem? How do we deal with that? The idea here is that the analysis starts with when you start collecting data. And the downside of this is oftentimes we'll get a set of data and then do a Pareto and then try to drive forward with that. I think that's reversed. We need to think about, well, what data do we really need? Not just what happens to be available, but what data do we really need in order to take action to make improvements or make changes or to learn something from this analysis. Then go get the data. And it may be available already, and that's wonderful. Or you're going to have to do some work to get the right kind of data for the decisions you're trying to make. And I'm probably going to harp on that a bit too much today, but it really goes that you have to have good information or good data to start with in order to create the useful information for you. The basic plot is, I like to call it just an organized bar chart, right? We have here I've got just completely fictitious data, and you might notice that it's 128 and 64, and power supplies are 32 and so on. It's just a simple doubling progression. And it doesn't quite fit neatly the 80-20. The CPUs and the hard drives on this one are almost 200 of the total counts that we have. And that's more than 20%. But that's just this piece of random data. The idea that I think most of us focus in on with these charts is, well, in this one, this particular instance is that most of our issues are with the CPU. And power supply is off the hook. We solved all those problems yesterday. They're all good now. Now we're going to focus on CPU. Well, what about the CPU, which is not enough information here really to know what to do about it. So now it's what causes the CPUs to fail. And there may be hundreds of those particular causes, but we're hoping that this basic 80-20 thing works and that a handful of issues really account for the bulk of them. And then we go fix those. That's great. It's the basic application of these things. And it's basically create your categories. I suggest highly thinking through how you're doing that. And then also, what's the count? What's the value that, what is considered a bad CPU, for example? Now, I've run into plenty of organizations that have, and you may have heard of it, is no trouble found or no fault found. And the Pareto month after month after month is the biggest contributor to field returns is this mysterious no fault found. And it might be 25, 30%. And I've seen some organizations even higher. And they say, well, there's no fault found, so we're not going to investigate that or work on it because there's nothing there for us to work on. The computer came back and it powered up and it works just like it should. Which begs the question in the failure analysis world of, well, why did the customer send it back? Are we evaluating it a way that the customer is not evaluating our product? There was something about it that said, I'm going to go to the trouble of stick this back in the box and ship it back to you or take it back to the store. Customers tend not to do that just for fun. I'm sure there are some that, maybe bought 3 computers and they tried them all out for a couple of days and they took 2 of the 3 back. I don't know that happens a whole lot. with some product lines. Clothes, yes, that happens quite a bit. I don't know how many pairs of shoes I try on before I find the one I want, but I don't go buy them and then ship them back, and which would lead to no trouble found, right? But let's say with computers, if the I got myself sidetracked with shoes there for a second, but the idea is that think through those categories of what it is at an actionable level for you. And it may be a cascade. I've talked about that. The issue is that it's just a count, right? Oh, I remember what it is the no trouble founds. I spent time with one organization, they had like almost 50% of their field returns were no trouble found. And we dug into it a bit, and it was things that were considered, the computer itself worked just fine, but it was missing a cable, or it was missing the mouse, or it was the on-off button was hard to find. It wasn't that it didn't work, it was just difficult to find. It was kind of under the left foot pad or some strange place for it for whatever reason. There wasn't anything technically wrong with the machine if you knew how to use it. If you didn't know how to use it, then it wasn't worth keeping and it got shipped back. It wasn't doing what the customer expected. And so sometimes what we count as failures, if my boot up time of my computer was back in the old days, 10, 15 minutes, today a customer would say that's totally unacceptable. If I turn on my computer, I need it to be on like almost immediately. But the computer itself just works just fine once it boots up. So sometimes we set our barriers to getting good information by how we expect the computer to use, irregardless of how the customer expects it to be used, for example. And so understanding what classifies a product to be say a CPU fault, if we get a field return, is as important as, do we have the right bins? Is, well, what classifies it to be a failure? Is it include the no trouble founds, and that's a different thing, or do we categorize that as a separate group? And are we going to look at that and understand why customers are returning it? The issue is that, well, what if it's just that interaction between the CPU and the hard drive? This particular brand of hard drives doesn't like working with this particular brand and particular individual CPU that we have. Maybe the two have timing problems on some percentage of them. Where does that show up in a chart like this? It could be random. One person would blame the CPU and the other person doing the diagnostics would blame the hard drive. So how is the data collected? What is classified as what's counted and what's not counted? And sometimes what's not counted is actually more important to go solve than the things that we do count. Let's see. Carl's, yeah, I think, or Bert's reflecting that thing is, yeah, details on the return reason is important. Yeah. Oftentimes customer returns and says, well, it doesn't work. That's kind of frustrating. And we put it on the bench and it comes up just fine and looks all just perfectly good. Maybe they had a bad power or wall power. Maybe their circuitry in their home is running at 80 volts versus the expected 120 volts. And our power supply says, well, that's too low. We're not going to power on. It could be an infinite number of things if you think about it long enough, I suppose. Yet, how do we solve those kinds of problems? And it starts with by being very, very clear with how you collect the data, what counts and doesn't count, and what kind of categories do I need to use such that I can take action on it in some form or another. Those are all key fundamentals, I think, to using these charts. I found that I've gotten casual with this and I have some data and I say, oh, I wonder what what's the most important thing here? And I'll put a Pareto together. And I always have to catch myself and step back going, well, what are we counting and not counting? It's probably by a bit of skepticism after seeing one too many very poor field failure analysis teams um, collecting the data. And we'll talk some more about that in a bit. Now, the chart can be enhanced a good number of ways. Um, and one of them, I think I mentioned in the slide on the, or I didn't mention, but it was noted on the last slide, is instead of doing just a straight count, well, let's say that that CPU costs $1,000 and the hard drive only costs $50, or vice versa. Let's say it's a very expensive hard drive. If we multiply these by the cost or the consequence or some other factor, usually related with cost or expense, um, that may change where the priorities are. If I can solve, one or two things that are way on the tail of a Pareto, yet they cause catastrophic bad, let me just put it bad outcomes and actually harm people, or they explode, or they do some other really bad thing in the safety realm kind of stuff. Well, I don't need to wait until that problem becomes the most dominant count of issues. I think we'd be out of business by then. But it comes down to that we're looking at the analysis of what's most important. And many will argue, and I included, will say, well, if it's a safety issue, even if it has the remote possibility to occur, you probably need to address that. Not probably, you need to address that. You need to solve that problem. If it shows up in your Pareto as saying these 8 displays all caught on fire, and the CPU ones just required a reboot, well, let's go fix the display one. There shouldn't be any argument with that. So adjusting how you weight the different categories and multiply their counts by something is a good way to capture what's important, either from cost or from safety or for some other factors or reasons. And the common sense stuff on creating a plot is label the scales or label the axes. You could do frequencies, you could do counts, you could add the count number to the plot, you could do a cumulative plot. There's all kinds of variations to this. Yet it's a tool that we can manipulate in order to tell the story that us and our teams then can take action on. And so just creating a chart to admire it is fun when you're learning how to do these things. Yet it's not all that useful when you actually need to make some decisions and allocate resources. So there's plenty of ways to enhance these things, make them pretty fancy. Please don't make them three-dimensional or twirling or just because you can. It's usually pretty distracting and makes it harder to interpret what's going on. It should be clean and clear, whichever version of enhancements or features you want to put on it, but not silly is the way I describe those plots. Just because you can doesn't mean you should sometimes. All right, let me take a quick pause here for a sip of water. Let's see, I'm seeing all kinds of stuff here. Carl and others are going. Let me open up my chat a little bit bigger. Any great success stories where you got the team aligned and it just did the perfect thing for you and you saved tons of money and you went on and had a great day, all those kinds of things? The one I'm thinking of is in a development process, and we were using a FRACUS system, failure reporting and corrective action system. It was a hardware, software, electronics, mechanical kind of box. And so there's a handful of different disciplines and teams working on it. And we get together every week to go over what are the types of issues we're seeing and what's going on with that. And one of the things we started doing is as the issue was focused on and we got to what was the cause? What was the piece of information that was missing that allowed us to that the design failed for us for some reason? One of our prototypes failed, or there was an issue that we needed addressing, all those kinds of things. And what we found was that, and this shouldn't be any surprise to any of you, is that we had incomplete set of specifications. So we didn't realize a handful of different things occurring until we actually got a physical prototype going and started evaluating it and testing it and so on, that, oh, this doesn't work. And the underlying cause over and over again is that the initial set of engineering requirements were kind of still very fluid and changed it wasn't locked down yet. And so what I designed last week isn't going to meet today's requirements. So the change management process for the requirements document was creating a lot of waste and a lot of rework on our design efforts. But it was that realization when we started going, why are we getting all of these kinds of failures? And it wasn't because of bad manufacturing. It wasn't because of bad design work or anything else, is that we had a moving target. And that showed up easily when we started going, what was the underlying cause for this? Oh, the requirement changed. And that showed up quite often as we started looking at why we had this particular failure. And even though the design in and of itself worked, by the time we got the prototypes, it was perfect design for the wrong thing, which was kind of frustrating. Let's see. Carl's got some examples going in there. Okay. All right. Now my favorite part. This is where I get to do the rant a little bit more than I have been already. As for a simple tool as it is, there's some things we do really need to keep in mind. And one of them is, and I've mentioned it a couple of times, is think through the data that you're collecting, what counts and doesn't count, and also what categories are you dropping these into? Are they overlap or not overlap, and so on. But let's back up one other step, just into the straight measurement error. If we've got really poor measurements, or we have a process, and I call it a shotgun approach. This is where the repair center, say for that computer, is, well, if I replace the CPU, I have to undo all these connectors and then reset all those connectors with a new power supply or with a new CPU. And voila, it's working. Now, was that a CPU problem or was that a connector problem? We won't know. And if we only keep track of what parts are being replaced, then we won't ever catch that bad connector that is intermittent or doesn't latch correctly or is works itself loose over thermal cycling or whatever. The other variation of this is that I'll open the box and I replace the 10 most likely things to have caused the problem. And I may even have a checklist or a sheet that says, if I have XYZ symptoms, then I need to replace these 5 or 10 components. And it's very likely that it'll solve that problem, which is great if you want to make very fast repairs. You want to turn it around real quick. And you may have done this yourself, is, what are the likely things that could cause this failure? We do a quick brainstorm, or we have experience with this, and saying, well, since I have it open, I'm going to replace everything I think of that could cause the problem, because it takes a lot of extra time to close it all back up and reboot it and do the diagnostics. Or it just takes extra time to do diagnostics to figure out what is the actual piece I have to repair. The other piece of this is that just because that component failed doesn't mean it was the cause, right? If my CPU is failing because of an erratic power supply, and I put another CPU in there, it's likely to fail again relatively quickly. Now, do I yell at the CPU vendor, or go looking at why my ASICs all failing? Only to find out with a deeper analysis that it was really a bad power supply sending way too many volts and amps at the wrong times. The problem is in how we collect the data and what we count and don't count. And that's really the fundamental piece of any analysis we do. And even more so in Pareto, where we're doing something quick and easy with the Pareto analysis, the charts. What goes in bins and how do we count them and so on is usually overlooked in way too many cases. So it's keep in mind that the data that we're getting has to be good in that it's uh, categorized correctly, that it's labeled correctly, that this is the cause of this failure, or this is why the customer returned it. And we had some reasonable information about that. Now, you could do it on symptoms, reported symptoms by the customer. And as you can imagine, there's going to be variability in that and just what they call, everybody might see the exact same symptom and have 10 different names for it. Well, that makes the data that we're getting a bit muddy. And so taking care to analyze what information or what data sets you're actually working with and how do they come to be. If you didn't design it, it's worth the extra effort to go figure out where it all came from, because it's very quick to get a really bad result if you don't have reasonable information or reasonable data coming with it. Yeah. Let's see. Bert saying technicians with the handover method. Usually the problem is under where my hand covers this part of the PCA. Yeah. There's been a handful of studies, and I've seen a couple of them where, and one of them was Pat O'Connor talked about it. In his days in the military, he was a radio repairman, and they were charged with turning radios around so they didn't have to be manufactured. We could repair and put a radio back into service much faster than creating a new one. And so their task was to repair as many radios per day as they possibly could. And he said one of the nuisance pieces of the whole process is that they had to fill out a form. Now, the form had the serial number, the model number, handful of other pieces of information, and any components used in the repair, because that was part of the billing. Their shop got paid basically by how many radios and what kind of components they were using, plus a bit more on it. So that was important. If they didn't do that, they didn't get paid. Then on the bottom half of the form was the collection of failure analysis type information. Well, what component failed? And there was a checklist of all the major components within these radios. And what Pat mentioned was that it was pretty common that it was the one right under your signature. You finished off the part that you are certifying that we fixed this serial number, and here's the components we put into it, and then here's the cause. And it was independent of what they actually did. It was whatever was closest, because the lower part of the form had no impact on their work or their effort or their priorities at all. And he said you didn't always want to pick the one right under it, so you would randomly pick something else on occasion. But he knew that the data went somewhere, but they never ever heard of it again. It didn't affect them one way or the other. It was completely random of what was being reported as being the cause of the failures. And so he had a pretty hefty distrust of the data sets that were being collected that went into things like Mail Handbook 217 and others. And I've seen this in person, is this where the repair team says, well, it's almost always this. Okay. How do you know that? Well, I almost always repair that. Okay. Why do you almost always repair that? Because I know it's almost always that problem. Okay. kind of a circular logic there that's self-supporting, but not informative. It might be years of experience and they really, really know that system, or it might be a self-fulfilling prophecy. It might be that it really could be an intermittent connector somewhere in the system, but by replacing that motherboard, you redo all these connectors and the problem goes away. So you falsely attributed it to a poor circuit board when it's not really its fault at all. It has to do with more of the cabling and connector choices that were made in the design. Understanding the details is critical to getting good information out of the analysis. So really look carefully at how it's put together, and our ability from technicians and repair folks and so on generally don't have a priority of getting good failure analysis data or root cause data. They're there to fix it and or get it back on the shelf. And unfortunately, there's a breakdown there that's systemic. And so if you're dealing with that kind of data stream, is be very, very conscious of it. The same applies about anything else you can pick up randomly on a database. Is where did it really come from before you go making any $1 million decisions? The other consideration here is, do you want to, some things are really easy to fix. You know, if we're looking at a computer system or a factory, it might be really easy on a factory floor to put the spare parts near the equipment that we have. And so that the and or redesign the equipment so that the operators of the equipment can make the repairs themselves. And snap in, snap out the faulty components rather than having an electrician come in, is make it easy. I'm thinking like inkjet printers. We can change the ink cartridges. Now, if I had to ship that off to a repair center or something like that, it would be very costly, and I would probably use some other solution for printing. But if I can do it myself, even though those print cartridges are really expensive, it's a benefit to me. I don't lose the printing capability while it gets off to some other place to go get artistically replaced by somebody that really knows what they're doing. Instead, the design team actually said, well, let's make it so the customer can change these things, make it easy for them. Now, the same applies in design for repair and design for maintenance, is let's make it easy. The other piece of this is that if you look at a Pareto and say there's a middle section of your chart, that's a whole bunch of stuff that are really easy to solve. The cost of the design change or the upgrades or the whatever it is that resolves those issues, or bulk of them, may be pretty trivial. Well, let's go do those. Those are the low-hanging fruit. Those are things we can just claim the benefit of, even though it doesn't solve the biggest problem. Another one is that all of these causes, like on the computer system, and here's where I go back to the power supply, is, well, maybe I've got some really dirty power going across my system. What if the underlying cause for all of these component failures and diodes failing and capacitors getting blown up, kind of seemingly random across our system, might be all tied to a common cause, faulty power to them? Well, let's fix the power supply, even though it's in and of itself not the top of the Pareto. Yet it may solve many, many problems for us. So getting to where's the true root cause, or as close to it as you can get, helps you identify these things that could have common sources of the issues, inconsistencies, and problems. And so some of it is, where do I get the biggest bang for the buck, so to speak, or the benefit, the cost balance, the cost benefit balance? In the chart itself, it doesn't always give us that information. And so a little bit of common sense and thinking through and understanding what's possible and where the connections are and the interrelationships are and where the safety issues are helps us then make the series of decisions in that analysis that give us the biggest benefit of using the analysis. And the last one is we really need something that we can take action on, right? We can do all kinds of cool analysis. I was interested in ice cream and which flavors were the dominant sellers. And there some vanilla and chocolate definitely are outselling most everything else. Yet they don't account for 80% of the sales. I guess we have a broad and varied taste when it comes to ice creams across the palette. Might be all 32 flavors fault, or it was at Baskin Robbins, I think, that always advertised 32 flavors. They almost always had vanilla and sometimes more than one kind of vanilla. So it diluted the vanilla by having variations of the theme kind of thing, but I digress. The idea is that if we can use a Pareto chart for lots and lots of data sets, that's nice. That's a fun activity, and it's a great way to learn how to use and build these charts. The real thing in our day-to-day work is let's think through the data sets that we are collecting such that we can take action based on the results. And it may be because it's cost loaded or severity loaded, or it may be at the component level, or it may be at the failure mechanism level. The tool is very, very flexible. There's no doubt about it. Yet you start with what it is that you need to decide. What's the decision you're trying to make, or what, and it may be related to prioritization. That is perfectly fine. Yet if I don't collect the right kinds of data and bin them in the appropriate ways, I can get a very different set of prioritizations. And sometimes that prioritization may be just go do another analysis. So if I really need to know what I need to do to fix this computer system, then I need data at a level that actually makes a difference and allows us to take action on it. Narrowing it down to the major subcomponents is the first step. Granted, that might be all you have available, yet it's probably not enough to actually make meaningful changes to the design or its manufacturing. And so, and you've heard me talk about this many times over the years, is start with what you need, what decision you're trying to make. And this is one of the many tools that we have available to help us focus or prioritize. And it works when at the end of that analysis, you and the team know what needs to be done. And we have in what I call actionable information that we can go do something useful with. 31 flavors. Thanks, Murray. You know, it's been a long time since I've been to one of those. I don't even know if they're still around. And one of the last thoughts here is, so once you solve the top 20% of the causes, have you ever then recollected your data over the next period of time to see if you really solved them or not, right? That's a common practice. And then created another Pareto. It's very likely that you now have 20% of your causes leading to 80% of your failures. Now, if you did it right, there's going to be a whole lot less failures. But does that process ever stop? And I guess that is one for you and your organization to consider. Well, when do you stop solving the vital few? And where's that process stop? Or does it? And that might be an indicator to your particular culture of your organization. And see, last question I got for you is, what other tools do you use? And I'll see if I can catch up with some of the comments that have been flying by. Yeah, Shahid, the video is being recorded, or the webinar is being recorded, and hopefully later today I'll have it posted up at Ascendo Reliability, underneath the Ascendo Reliability webinar series. And it's sorted by topics, and I'm trying to think of where it'll be, but also we'll have it in the newsletter, a couple different ways you can track it down to where it is. And if you have trouble finding it, just let me know, and I'll see if I can, well, once I have it posted, and then I can send you the link. But it usually takes me a day or two to get that done. Yeah, Carl's makes the observation that the Pareto principle, do more with less. There's some argument with that I think the lean organizations tend to look at it that way. What's the most efficient way we can do stuff? I don't know if that's connected to the Pareto principle or not, but I've certainly seen that run around. All right. Not seen any other tools, but I'm kind of leading to that Pareto is one of those basic quality tools. I think there's some argue 7, some argue 8, like histogram. If you take the same exact data you have, if it's variables data, well, use the histogram. It's a much more useful tool to understand what's the shape and spread of this data. If it's categorical data, the Pareto is often a good tool to use, or a simple bar chart. There's other tools though, like FMEA. What are the risks that were involved, or a hazard analysis? Pair that with your Pareto and looking for those safety issues so they don't get swept into the long tail, for example, and ignored. Plenty of others, plan, do, check, act type stuff all applies with Pareto. So plenty of other tools that we can use in conjunction or in sequence with the Pareto analysis. Obviously, failure analysis is a big part of it. All right, well, I'll stay on the line if there's any other questions and so on. Thanks for considering some of the fundamentals of Pareto analysis. And as usual, I completely forgot what I have planned for next month. If you have any ideas or suggestions, I'm always open to topics you'd like to talk about, and just let me know. But thanks so much for attending.